Hello, everybody, and welcome back to our discussion on Chapter 8. In this lecture, we're going to talk about the formal charge on an atom in a molecule. A formal charge is the charge that will be assigned to each atom in a structure by assuming that the structure's electrons are divided equally between the bonded atoms. Most Lewis structures do not require any formal charges. Structures that will require formal charges, however, can be recognized by the number of bonds made by the elements. Typically, carbon forms 4 bonds, nitrogen 3, oxygen 2, and fluorine will form 1 bond. If the Lewis structure requires more than these, the atom will have a positive formal charge. If the Lewis structure requires less than these, the atom will have a negative formal charge. The formal charge on an atom can be calculated from this equation. We take the number of valence electrons, this is found off the periodic table, we'll subtract the number of lone pair electrons, and then subtract half the number of shared electrons. So let's look at calculating the formal charge on each atom in this molecule, carbon monoxide. In carbon monoxide, we need to take a look at each atom individually. So using our formula, we look at carbon, and carbon will have 4 valence electrons based on the periodic table. So this here comes from the periodic table. And then it has 2 lone electrons, these 2 electrons here. And then the 3 bonds here each have 2. So with 3 of them, there's a total of 6 electrons, so we take half of that. The formal charge of carbon and carbon monoxide is -1. Oxygen, what we look at is oxygen will have 6 valence electrons off the periodic table. It has 2 lone pairs, and again, it will have 6 bonding electrons shared with carbon, and it ends up having a +1 formal charge. Let's try by building a structure, Lewis structure, for the ammonium cation. So to begin, what we need to do is draw out the skeleton. So here we'll have nitrogen, and it'll have an H coming off of each side. Nitrogen's our central atom. Then we need to figure out how the electrons will play out. We have 4 hydrogens, and each one will give us 1 valence electron. We have 1 nitrogen, and each nitrogen gives a 5, so there will only be 5. It has a +1 charge, the ammonium ion, so we have to subtract an electron from this. So 9 minus 1 will be 8 electrons. And if we look here, nitrogen has 2, 4, 6, 8 electrons around it. So all of the electrons are being used. Now to calculate the formal charge, we want to calculate the formal charge on nitrogen. That would be 5 valence minus the lone pairs, which nitrogen has none. And you're going to take half of the number of bonded electrons, which is a total of 8, and you get a +1 charge. You could do the same thing for hydrogen. The hydrogen has 1 valence, has no lone pairs, and half of each hydrogen is 2, because hydrogen will only share 2 electrons here with nitrogen. So that ends up being 0. So each of these hydrogens are zeros. Let's take a look at the nitrite ion. And in nitrite, we can see that it's NO2 minus 1. Nitrogen will have 5 valence electrons. Oxygen will have 6. So the formal charges, the one on the left, if we drew the equation like this, is a -1, 0, 0. And here, this would be 0, 0, -1. So you'll notice that when you take the formal charges and add them up, it equals the overall charge of the compound. So both structures will have the formal charge, and therefore either structure is equally favorable. In the next lecture, we'll talk about what this is called when you can write two structures like this. So this is the next lecture. We'll define what this is. When we look at H2CO, total valence electrons will be 12. So we will have the C bonded, double bonded with the O, and hydrogens each bonded with the carbon. Or we could have the C double bonded with the O and the H is coming off of the oxygen. So taking a look, if we did the calculations for this molecule here, each hydrogen will have a 0 charge. The carbon has a 0 charge. The oxygen has a 0 charge. Down here, if we use this structure, hydrogens have a 0. Carbon has a -2, and oxygen has a +2. Structure A has the smaller formal charge of all the elements, and therefore it's the more favorable arrangement. So the goal of formal charge is to have the smallest formal charge on each atom. That's the whole goal of using the formal charges to identify appropriate Lewis structures. When using the formal charge to predict the most stable structure, structures with the smallest formal charges are favored. Structures that have adjacent atoms with formal charges of the same sign are much less favored. Structures that place negative formal charges on the more electronegative element are favored. And formal charges of opposite signs are usually on adjacent atoms. Oxidation numbers are assigned or calculated based on known fixed positive and negative charges and can be determined by examination of the formula. Oxidation numbers are useful to identify how charges change in a redox reaction. To see how both work, formal charges and oxidation charges, let's take a look at chloric acid, HClO3, and see how its charge distribution would be described using both the oxidation number and the formal charges systems. So here, with looking at the oxidation numbers on chloric acid, we know that hydrogens will have a +1 and oxygens have a -2. So to find the charge for the chlorine, we have a +1 charge, we have a -6. Since this overall charge is neutral or 0, then we need to make sure that whatever chlorine is can be added to a +1 to cancel out the -6. So chlorine must be a +5 in order to cancel out the -6 charge from the oxygen. Here we look at the Lewis structure using our valence electrons. So from each element, this is the valence electron, 7 from chlorine, a total of 18 from oxygen and 1 from hydrogen. It's a total of 26, so half of that's 13 pairs. We make our skeleton. We fill in the terminal elements with the lone pairs and make sure that each element has 8 electrons around it, except for hydrogen, which is happy with 2. So if we look at the formal charges now, you'll notice that using our formula, hydrogen is 0, oxygen is 0. One of the oxygens attached to just the chlorine is a -1. Another oxygen attached to the chlorine is a -1. And then the chlorine itself is a +2. Chlorine in oxidation numbers is a +5, but in our formal charges is a +2. Finally, both oxidation numbers and formal charges must add up the same way. Even though the numbers may not be the same between both systems, when you add up oxidation numbers or when you add up formal charges for compounds, they must be neutral. So all of the oxidation numbers must equal 0 and all of the formal charges must equal 0. For polyatomic ions, which always have a specific charge, the sum of all oxidation numbers or the sum of all formal charges must equal the charge on the ion. So here's another example with sulfuric acid, the oxidation numbers are +2, +6, -8. That's for hydrogen, sulfur, and oxygen. But if you look over here, our formal charges are based on each individual element. Hydrogen 0, oxygen 0, but this oxygen here is a -1, as well as this oxygen. The sulfur in the center is a +2. The oxygen on the outside is a 0, and our other hydrogen is a 0. You'll notice with the oxidation numbers and the formal charges here with sulfuric acid that if you added them all up, each of them would equal 0. And this is something that's very important for you to keep in mind. Even though oxidation numbers and formal charges may not be the same for each individual element, for the overall compound or polyatomic ion, the formal charges and oxidation numbers must add up to the same value. That is the end of our formal charge lecture. The next lecture we're going to talk about resonance structures.